Okay, that's what I'm going to talk about today. So I guess if there's nothing else, I'll get
Yeah,
started.
let's go. Let's go. Great.
Okay. Um, Let me, first of all, okay, that's what I want to bring up. Let's see, to get rid of the stuff on the side of the PowerPoint, what I need to do, I think, is slideshow. Is that what I need to do?
Yeah, slideshow. There's a hotkey for that, but I always forget.
From the beginning, I guess.
I think it's F5.
There we go. Okay, now I don't want full screen. Okay, I'm going to share that. Oh, interesting. When I got out of full screen, it came back the other way.
Got it.
Yeah, the sidebar comes back magically.
Yeah. Let's see. Try that again. Slideshow from beginning. Okay.
There we go.
I guess I'll deal with the full screen thing. Okay. This is Energy Futures Part 5. It's part of a series I've been doing over the last year. The other sources of electrical power that I've talked about were coal, nuclear, water, and wind. So now I'm talking about solar. And I'm going to start out with comparison of the different sources of electrical power, and which is what I've done the last few times. But then I'm going to have a slight update because I have more more information from the last year or two, and then get into the specifics of what's been going on in solar energy. So these are a number of the different sources, renewable energy sources and non-renewable ones. You've seen this graph before. This has many of those sources from the previous page. And the yellow one down here at the bottom, where's my, can't find my cursor. Oh, there it is. Is solar panels, photovoltaics. So it's up to 2023, it was the second most affordable one per unit of electrical power. Wind was cheaper. Natural gas was next. So this is why there's been a lot of growth in wind and solar renewables, because they are cheaper. This explains the calculation from the previous graph. We can skip over that. But what the graph is called the levelized cost of energy. Here is a comparison of a number of these sources, and PV stands for photovoltaics. This is utility size, this is residential, like house rooftops and so forth. In most measures, this is the cost of the levelized cost of generation of the power. And you can see that photovoltaics generally are pretty low. I'm not sure why this one is very different from all the others. But here's another measure. This was done in Poland, looking at their electrical power. And hydro, wind, and solar were all very similar in price, with what they called brown coal. next. And the hard coal, which is more expensive here in the US also, more expensive. So generally, not only in the US, but around the world, the renewables are cheaper than the fossil fuels. This just is a list of things you can look at to compare the different sources of power production. And basically, all the non-renewable resources require all of these phases. There's infrastructure, there's production of the source, like coal. They have to mine the coal and store the coal, and in the case of oil or gas, there's refining involved, and distribution of the source to get it to the power plants, and then the use of it and the byproducts of that use. So all these phases are present and have some outputs for non-renewable resources. Renewables require phase one, there's some infrastructure. Hydro, wind, and solar do not require processing and refining of the resource to make it usable, so there aren't any byproducts there. Also, wind and solar don't require storage of the resource. I mean, you don't store the wind or the sunlight, you just use it. Because the renewable resources are a little more straightforward, they generally don't have to be mined or something like that. Water's a little bit in between. They tend to be easier to use and cheaper. Okay, we don't have to talk about this much. I just want to mention that solar and hydrogen power produce direct current. Everything else is used to turn turbines, and that produces alternating current. So in a way, for many things, solar can be preferable because of that too. For example, if you're going to use direct current to operate any of the IoT, Internet of Things, all these electronic devices use direct current. Okay, so let's see, I think I'm going the right direction. Yeah, so this is the use as of 2023. By far, the most used resource is natural gas at 43% 2 or 3 years ago. Nuclear was second, 18%. The renewables have been slowly catching up, but they're still pretty far behind. Wind has been around for a long time, and so it has a lead there among the renewables. And hydro, we've had dams and so forth for a long time. Solar at 3.9% 2.5 years ago has been growing the fastest though, and it's catching up. So as of the end of in 2025, measurements were made and on the output. Wind and solar together reached a record 17% of US electric power. And coal dropped to a historic low of 15%, down from 16% a year before. Wind and coal up from about 14% to 17% of our energy output. In 2018, coal was 3 times larger than the combined total of wind and solar. So there's been a real shift, mostly because coal is not only dirty, but it's expensive. That's the main impetus for the change. So the growth, percent growth of the from 2024 to 2025, 27% for solar. That's pretty fast growth. And wind plus 7%, natural gas plus a little over 3%, coal fell by about 3%. The story in 2025 is a little bit different, and I'll talk about that just in a minute. In terawatt hours, solar added 64 terawatt hours in 2025 compared to 2024. Natural gas added 59, wind 32, and coal dropped by 22 terawatt hours of power. So you'd think we'd have fewer emissions because we're using the solar, natural gas, wind more than we are. They've increased more than coal and the non-renewables, such as gas. Well, the emissions have gone up because total demand has increased by quite a bit. And so we're using more energy. So total emissions are still up, but the growth, the percentage is down per terawatt hour. Does that make sense? Okay, here is a chart of the change from the first 4 months of 2024 to the first 4 months of 2025. And you'll see that solar power generation increased 33% year over year for that period. Hydro increased 24%. What's surprising is that in 2025, the first 4 months of it, that also increased by 24%. You'll notice that natural gas went down 6%, and that's why the coal went up. It's because the price of natural gas spiked in early 2025. So people stopped using it so much, and they turned to their most readily available resource after that, which was coal. And that's why coal use went up. That's not going to last, but there's an interesting spike there in coal use in the first 4 months of 2025. But solar is still outpacing everything else as far as growth. Okay, now we'll get into photovoltaics themselves and the technology that's been going on. The first item I have there is perovskite silicon tandem cells, silicon and perovskites together. If you layer perovskites, and I'll get into what they are in just a second, on silicon photovoltaic cells, the cells capture more of the solar spectrum, so that breaks the single junction efficiency limits, and it can get over 33% of certified efficiency. That's pretty good. And that blend of perovskites and silicon lowers costs and promises more flexible applications. Perovskites have one problem. Well, yeah, that they're a little bit susceptible to heat and water. So there are ways that are being looked at, get around that so that they last longer. Perovskites were discovered in the Urals in 1839. They were named after Lev Perovsky, so perovskite. He was a well-known geologist back in those days. What it is, it's an orthorhombic calcium titanium oxide material. So in this formula here, this is calcium, titanium, and 3 oxygen atoms make up the molecule. The name perovskite can also be applied to the class of compounds which has the same type of crystalline structure as the calcium titanium oxide. And that's known as the perovskite structure. And it has this chemical formula. So A with 1 free electron, B with 2, and X with 3 holes, because there's 3 of them. That creates a very crystalline type of structure, a particular kind. And the halogen perovskites are the ones that are typically found in modern photovoltaics, photodiodes and solar panels. As I mentioned, a weakness of the perovskites is that it degrades faster in heat than silicon does. Graphene. Everyone knows what graphene is. I assume now it's a single layer of carbon atoms in a kind of a lattice structure. Yeah.
Are perovskites manufactured or mined, or both?
Mostly mined. I think they also can be manufactured.
Thank you.
They're found in the Urals. There's also some in Arkansas, and there's another deposit somewhere in Europe. I can't remember exactly where.
See, Dean has a question.
Okay, go ahead, Dean.
Yeah, when we were talking about costs, and you were saying, well, there are no byproducts with solar. Are they taking into the byproducts of the mining and the production of the materials? And also, does that factor in the lifespan of that particular technology, when you're talking about economics?
Yeah, if you're, let's see, I'm trying to figure out what you're referring to. The way back here. No.
Yeah, the costing, but you said, well, there are no environmental byproducts in solar and wind. Well, there are in the manufacturing.
In the actual production of it.
Yeah,
right?
all right. So
You don't burn wind like you do oil.
I got you. You're just talking about the production, not the manufacture of the particular technology.
Right. There's no refining involved, for example, in hydro or wind,
Right,
or solar. So
right.
no byproducts there.
But I mean, there are.
If you're talking about use and you're talking about the lifetime of the infrastructure, or what, yes, there are some byproducts there that you have to deal with.
Mm-hmm. Okay.
For example, the blades of wind turbines or solar panels and so forth. So yeah, everything has byproducts at the end.
I heard perovskite has an issue with lead.
Yes. Some perovskites have lead in them, and when you reach the end of the lifetime of that photovoltaic equipment, you have to deal with those types of things. Lead is one of them. Let's see. Okay. I was going to get into graphene. Adding graphene to perovskites shows promise for massive efficiency boosts. It can kind of almost double the efficiency. Well, at least 30% more efficient. And that can also create cost reductions in the manufacture. It can also eliminate the need for some of the precious metals that tend to go into photovoltaics, such as gold and silver, which are used in the junctions and things like that. So when you combine graphene with the perovskites, you end up with cheaper materials and cheaper manufacturing processes. Photovoltaic panels are being developed also that are self-healing and self-cooling. I have a space problem there, but I want to show you a video now that kind of covers these first topics, and it's pretty interesting because this is all fairly new stuff, especially the combination of graphene with perovskites. So I have to go find that. Okay. I think that's what I want. Okay, here's a video called What Solar's 2025 Breakthroughs Mean for 2026, which is the year we just entered. So I want to show that. This is, I have several videos by Matt Ferrell. Undecided is the name of his whatever you call it. So Undecided with Matt Ferrell. I like the way he presents these things because he sticks to the facts. He gives you a lot of facts, and it's a balanced presentation. So let me share that. Running out of space on my screen here. Okay. Can everyone see that?
PV Magazine.
PV Magazine.
And some record-breaking efficiencies in 2025.
All right, any questions on that? You went through that, a lot of information pretty fast. Go ahead, Dean.
Dean, you're muted.
I try to be muted. Was it just me, or does that guy talk on a microphone that he inherited from Edison? God, that was the worst audio I've ever heard on the internet.
Really?
Yeah.
It sounded good to me.
Really? Anyone else didn't hear that? Absolute
Maybe I
tinny.
need to turn my sound up.
Yeah, I don't know.
It was
A little blurry.
little different, but not bad.
But yeah, I mean, it sounded like it had a bandwidth of about like that, yeah. Yeah, like a really poor overseas phone call back in the day. Anyway.
So what is this Kesterite going to be? Did you get a chance to
I
take
didn't look into Kesterite.
Okay.
So it sounds promising though, because it's made up of all fairly common elements. So as far as its actual properties, I'm not sure how it compares. But that's something we could look into some other time if you want.
I really like the low tech gel on the back of the on the back of the devices. That's really appealing to me because you could retrofit that really easily, you would think.
Yeah. Okay, let me bring, if I can get to it. Let's see, where did my, oh, there's my PowerPoint there. Okay. All right, let me go back. Share that. Okay. So that's a couple technological advances already, the perovskites and the graphene. I pronounce it perovskite because it's named after Perovsky. Next we'll talk about bifacial panels. That's photovoltaic panels that work on both sides. So it's kind of interesting. Basically, these capture sunlight from both sides, and that can increase the energy yield by 10 to 30% in suitable environments, especially if you have reflective surfaces on the back side of these.
Like snow.
Yeah, yeah, or light colored grass or you know, whatever.
White roofs.
Yeah, if you're talking about roofs. So I'm going to show you another video about this, and it's another one by Matt Ferrell. So I hope the sound on this one's good. Okay. Can you see that?
No,
Okay, I guess I have to stop the previous sharing and start a new one. Share screen. Okay, can you see that?
Yes.
yes.
All right. Let me move this over here a little bit. Okay, this is how the back of a new solar panel just changed everything. That came up during the last video, and that is the question of heat. Since heat is lowers the efficiency of PVs quite a bit if it's excessive heat. That's why you don't see too many solar farms built in the desert. Okay. Yeah, why farmland where there's grasses and so forth is preferable as far as the production of electrical power. Okay.
Remarkable. The fact
I think that these solar panels paired up with the newer batteries, high performance batteries, just like it seems like a brighter future more overall.
Yeah, I'm not going to get into storage at all today, just the production.
Boy, that's a
Because there's a lot to talk about as far as advances in batteries. And I don't have time for that, but maybe some other time.
For my personal belief, not feeling confident right now with the letting the power companies excel determine how much of a return I'm getting on my battery or on my solar panels. It seems that having both would give you a little bit more of a secure performance on your solar panels.
XL is pushing back really strong to get rid of net metering,
So
which
what does that mean for the consumer then?
if you produce extra energy and you think you're going to sell it to the utility is now saying, we don't really want yours at extra money. You know, I mean, unless they get the price way down, because we're producing our own energy with solar panels and it's cheaper because we've done it in such a large scale.
Well, they pay you for your energy depending on the price at the time per kilowatt, right?
Oh yeah, I mean it's through MISO and all these other organizations, but what we're finding is more and more people are doing what Stan was talking, is trying to put in PV and put in batteries. And even XL has said that is by far the cheapest energy you can get. So we'll see. Anyway, sorry.
Yeah, I've had solar panels on my roof for, I don't know, 7 or 8 years now. I didn't get a battery because the batteries were very expensive back then.
Yeah.
Instead, I've been getting checks from the power company.
Yeah.
Yeah, which keep getting smaller. We've had ours for 12, 13 years now. And yeah, SDG&E says we don't want, it's not cost effective for us to be your battery. And they're encouraging you to, and of course there are advantages of having your battery, as in you can be immune from power outages, et cetera, et cetera. But you know, I looked into a Tesla wall way back when, and Jesus, it was as much as the panels, you know.
Yeah. Yeah, I would assume that battery prices have come down some too, at least per kilowatt or whatever.
Yeah, and they're way back then that there were lead acid, you know, because who cares about the weight sitting on your driveway or whatever, that were more cost effective, but you know.
Yeah, I considered at one time building my own lead acid wall, you might say.
Yeah, me too. We did too.
I didn't ever.
I'd worry about the dangers of such a battery.
Well,
It is. You got to have ventilation.
Yeah, well, it would have been in that storage area at the back
Yep.
of the garage.
Tom, the other thing about batteries that I'm just hearing now is that XL is putting in, they're saying maybe as many as 1,000 batteries in their system for storage of their own power, not necessarily renewable, but so that they can store up so that if they hit peak loads, they can end up, you know, using their own reserve and not start up peaking plants.
Right.
So that's kind of interesting.
Yep.
Yeah, peaking, mostly for the peaking, that's using natural gas, but the peaking plants are more expensive than the ones that run natural gas all the time.
Yeah.
So it's interesting how the economics works out. Okay, let me pull, let's see if I can find my. Okay. To continue on with the technological advances. We talked about perovskite, graphene, bifacial panels. Now I want to talk about BIPVs, which is building integrated photovoltaics. In other words, you can make structures where just about every part of it can use sunlight as energy. The windows, the walls, the roof, the floors. So I want to talk about that for a little bit. This is the facades also. The structural walls plus facades in front of the walls are often used. So I want to show you one more video about that. So I'm going to bring that up. Oh, this is not a video. this is actually an article that I want to share. Part of. And I listed this also, all these videos and articles I've listed on the meetup website, on the description for this meeting. So if you need to, if you want to go back to any of these, you can find the list there.
What was that? You said you can find the videos
The
where?
list of the videos and these articles on the meetup site and under
Meetup.
the description of this meeting. It's a very long list. There's over a dozen altogether. Okay, so now building integrated photovoltaics. There were a number of videos I found, but they all were pretty commercial and rah-rah for our company type of thing, so I didn't want to use them. So I want to just basically list the kinds of BIPVs there are. There's roof integrated. So instead of asphalt shingles or slate tiles, you have PV tiles forming your roof and protecting your house from the elements. So there are a couple different types of those. There's solar tiles and shingles. There's laminates and frameless molecules, which are modules, which are often used on pitch roofs and have lines like this, looking more like the standard rooftop photovoltaic panels. So that's roofs. You can turn your actual roof into a photovoltaic power generator. And on these vertical walls, the sides of your buildings, this would more often be occurring on office buildings and things like that. There's a facade and cladding BIPV, building integrated photovoltaics. There's the cladding, which are the actual walls. They would take place of the I don't know, the boards on the side of your house, but they're photovoltaic, so they can actually generate electrical power. Also, there's double skin facades. So on the outside of the outer wall, there'd be another wall that has photovoltaics. And this is sometimes referred to as a rain shield or something like that. So the walls of a building can be used as photovoltaic power generators. And the windows. You'd think that it'd be hard to see through a photovoltaic panel. Well, not if you make it right. They can have photovoltaics in them and still be not completely transparent, but semi-transparent or translucent, which would be ideal for like an office building, something like that. So you could have PV glazing where the cells are in the laminated glass or coated on top of it to let some light through, and converting the light that doesn't get through, capturing it to create power. And you can also have thin film or dye sensitized semi-transparent modules. The effect is fairly similar as a PV glazing, but it's a film on top of the glass.
2 well placed 500-pound bombs. How many shrubs could be on the 2 well placed?
Okay. Now, I mentioned the outside curtain walls that aren't actually structurally part of the building, but can be used on the outside. So these are like the somewhat like the panels that you might put on your roof these days, but these are vertical, put on, or nearly vertical, put on the outside walls, curtain walls. And there's flexible laminates. Now these generally are photovoltaics that can be printed using a special kind of ink on flexible surfaces, some kind of membrane. And they're used, can be used, well, as listed here. Canopy coverings, balustrades, awnings, and so forth. And we'll get into that, awnings and things like that, when I talk about fabrics. Okay. The BIPV-T systems couple PV electricity generation with thermal capture. So these are dual purpose. They can help cool or warm the building as well as generate electricity. Okay. See, I wanted to share this article. I guess this is it. So the benefits of, here are some examples. You can get all sorts of architectural effects using these things. But benefits are maybe improved aesthetics like this. You don't have a blank wall you're staring at. And then material and labor offsets. When you have BIPV replacing the envelope material, you're getting two things at once. You're getting a wall and you're getting power generation. You get more renewable energy on the site, which can reduce utility bills. And there are people who are specialized now in the design of HIPV buildings. So it's a kind of a branch of architecture. The trade-offs are potentially higher unit cost per watt compared with rack-mounted photovoltaics like some of us have on our roofs. And it's more complex detailing and integration. So usually there's some kind of architectural design going on there.
Tom?
Increase the prices. Sure. Who's that?
Could you help me out with when you said compared with, and I missed that next word?
I'm not sure which word you're referring to.
Like the old fashioned or what you have on your roof, or what was the word?
Yeah. What I have on my roof are the regular photovoltaic panels.
Okay, and is there a particular
and these
word for that, or just
these are more architecturally designed? They're meant to be aesthetically pleasing.
okay?
Okay, so I just wanted to mention that there's all these opportunities to put photovoltaics in lots of spots, and a lot of them are on buildings, houses, office buildings, plants, factory type buildings. So we're getting to the point where photovoltaics are showing up just about everywhere. And I'm going to mention a couple other places you'll find them too. Okay. Let's go back to here. Okay, I mentioned BIPVs. They can be anywhere in the structure. They can be in the windows, they can be in the walls, they can be in the roof. They can be even in the interior, in the floors, near windows. I want to talk a little bit about thin film and flexible solar. Yeah,
Can I just quickly share? I just wanted to tell everybody so they're aware. At least what I'm aware of in Minnesota, we have maybe 30 installations of the Tesla panels in the area. And then a company that MRES is contracting with is actually having them installed. But anyway, the other thing that's been really new lately that ties into what you were just talking about is that there's 47 houses in St. Paul that have just last summer were built by Habitat for Humanity, and they all have solar shingles. And they're GAF shingles that are guaranteed production and everything. So anyway, there's some local examples of exactly what you're talking about here. So it's pretty amazing that we've got that in our own northern climate area. So that's it. Thanks.
Yeah, well, in winter, even though the sun is low, sometimes the skies are pretty clear and you can still generate power. And in summer, you can generate a lot. My roof is not quite 45-degree angle, and I'm right about at the 45th parallel. So I can get pretty direct sunlight at the right angles on my panels in my house.
Yeah, that's one of the things with the shingles I worry a little bit about. They're going to build another home or another 100 homes there. And I don't know if they told me originally they were going to put up solar shingles and regular solar panels. I don't know, with if we get a lot of snow, just the regular panels will get rid of it fairly quickly, but the shingles, that could be a problem, I think. So
Have
anyway.
you seen those shingles? Do they look like they'll slough snow off?
Yeah, they're like I was been over to it's in the Heights in St. Paul. That's that major new energy center that's being built over there on the old golf course and highest point in St. Paul. And it's really interesting. We were going to add those houses to our solar tour that our group does every year. But we didn't because it was late getting people into them. So we didn't do it. But hopefully this coming year we'll have them on the tour. But yeah, it's really interesting. I mean, it's become so common, this building integrated stuff. So anyway, thanks.
Okay. Tom, you have a hand up?
Oh, for something, I thought you were going to be talking about fabrics, but you got fabrics.
Yeah,
So
they're coming up.
the question is, my hand is up for that.
Yeah, solar textiles I'll be talking about. Okay, but that's in a few minutes, not right this minute. Okay, next is thin films and flexible solar. So I want to talk about that. These are basically photovoltaics that can be printed on flexible substrates and quantum dots. And I'll explain what those are in these next two videos. So let me bring up the first one. Stop showing this.
A team of researchers out of MIT's
Okay, that's the video I want. Let me get it to the beginning.
solar.
Okay, that was short and sweet. That was from MIT, but that was 3 or 4 years old. So there's been more progress done
Yeah.
since then.
They answered all my question. I have solar powered tents, teepees, yurts, device chargers. Oh, and sailboat sails.
Yeah. As
You're a
far
mind reader.
as far as space, this could be really good for solar sails out in space, because not only would they provide propulsion from the light impinging on
Mhm.
them, but they would also provide power for the electronics on the
Mhm.
on the space vehicle. So there's a dual purpose going on there. Carol.
Yeah, all of this stuff about power per kilogram, that's nice, but do we have any comparison with the old-fashioned stuff on power per square area? Now, does it cost 3 times as much roof area,
Yeah,
even though it's great in per kilogram?
that the area that will depend on the efficiency of the photovoltaic thing itself, the silicon or the perovskite or whatever.
Yes, I know, but
So it'll depend on what materials it uses to produce the electricity, and I can't tell you. I don't have a comparison of all the different ones in one chart.
oh,
That's what you're looking
I,
for.
I'm just, I mean, I'm just wondering if you have to have, you know, 10 times as much roof to use this stuff, or
What's happening is that Tom, how much output are your panels per watt?
330, I think is what it is per panel.
Yeah, and now they're developing like 700-watt panels, and that is squeezed into a little bigger, but not a huge panel. And the other thing that affects is when you're talking about the cost of installing, it keeps down the soft cost, which is people getting those things on the roof, and so they can put one panel up, and it will take the place of what used to be 2 panels. So that's been a big help.
Yeah.
If that helps.
What I got was when I got the original, I got I think it was Panasonic panels, which were 10% more efficient than the other ones. So the other ones were 300, the ones I got were 330. But things improved over 5 to 10 years.
Just for what it's worth, when I started in this stuff 20 years ago, we put 880 solar panels on the Green Institute that were 45-watt panels. And that was the biggest installation in the upper Midwest at the time.
Eric.
Did you come across anything about the future practicality of the solar-powered drones?
There is one video that I think I'll be able to get to that talks about space generated solar power and beaming energy down to things like drones. I don't know if I'll have time to show that video, but yes, it is possible to do that.
Maybe also, I got
I'd really like to see that.
transmission costs. Any improvement in transmission costs? Because that's huge. Cameron used to tell me it wasn't practical to transmit power more than about 300 miles.
Yeah, I didn't get into the grid because that's kind of a whole another big topic too. I mean, whether you want to use AC or DC and all sorts of things.
Yep, the DC is a major change. Yep.
So I won't be addressing that today, but it is a worthwhile topic to look into at some point. Storage and the grid are 2 big topics that affect, of course, how you use electricity. And so at some point we'll have to look into that. Okay, next I want to talk about quantum dots. Quantum dots, maybe I should bring up my. Well, I don't have much about it. Quantum dots can generate current from a broader spectrum of light because the light frequencies that they're sensitive to can depend on the size of the dot. So they can handle a broader spectrum of light than silicon-based photovoltaics, potentially doubling their energy efficiency to around 60%. So they can utilize infrared as well as visible light and so forth. Perovskite quantum dots are efficient and less toxic than some other varieties. Right now, quantum dots are not very durable. They're vulnerable to heat, but they have been used in TVs for years. The QLED, the Q stands for quantum dots, QLEDs. So, but that's in a pretty benign environment in your house usually. So, yeah, I want to show another video. I have actually about 3 videos on quantum dots. I won't have time to show all of them. Let me see if I can pick out. I'll pick out the medium length one. A very good one is another Matt Ferrell one from his Undecided posts called "How Quantum Dots Solar Panels Could Change Everything," but that's almost 15 minutes long, and we're down to almost only a half an hour left or so, and I have a few more to show. So I'm going to show a shorter one, and this is how to achieve quantum dot solar power. Well, let me see if I can find that. Well, that's just talking about other applications of quantum dots, but since we're talking about photovoltaics and generating electrical power, I'll stop there. Just to go back to one thing we talked about 15, 20 minutes ago, the bifacial photovoltaics, where on the back side you can get also develop energy on the back side of the cells. Well, the quantum dots could be very useful there if you have, say, solar panels out in a field facing upward. You get the normal silicon looking at the sun, directly at the sun. The backside facing down toward the earth, where the earth is emitting infrared heat radiation, would be very good to use quantum dots that are tuned to absorb that infrared wavelength. And that could be very useful for two-sided panels. I would recommend seeing the other 2 videos that I have listed on quantum dots. They're both by Matt Ferrell. One's how quantum dot solar panels could change everything, and the other is called Nanoscale Solar Massive Output. Go ahead, Carol.
Yeah, I would really like to see the one you talked about earlier with applications for solar power from space. And
Okay,
if you
we have
don't,
about half an hour, right?
if you don't have time for that, could you put a pointer to it out?
Yes, I will. I have 2 or 3 more topics to cover before I get to that, so we'll see if I can get to that.
Okay,
But I would like to get to that.
that's one of my fond areas.
Yeah. Doug?
Just a quick question, Tom. I looked at those topics that you had listed, and there's no video links to them. Is that
No, I didn't put because some of the links are very long, some of them. You can Google them with the
Yeah.
information I gave you and come up with them.
Okay. All right. I was just checking. Okay. Thank you.
Yeah. Stan.
I had the same point. I was looking for video links on those files.
Yeah, sorry I didn't do that. What I had been doing is putting all the links in my presentation, but then you said, well, that's not useful. I can't cut and paste that. So I didn't do that when I put it in the meetup description either. Next, I'm learning. Okay. What's next? Okay. Let's pull this up. Okay, we've talked about all these topics on this page. Let's go to the next page. Some technological advances in AI and smart systems. I'll mention that for just a few seconds. AI can be used to optimize the performance of these, and as well as the design of these photovoltaics. And smart systems can improve grid integration and energy management. So, when do you store the energy? When do you send it out on the grid and so forth? Nighttime generation is kind of what we talked about when we were talking about the bipolar. I mean, the two-sided panels. Infrared heat radiated from the Earth at night can be used also, especially using quantum dot type technology on the backs of the panels. Okay, I want to talk next about solar textiles, which I think Tom was interested in. So there's you can use photovoltaics in sails for boats, for example, or weather balloons, or canvas shelters or awnings, like heavy materials that are used kind of structurally. But you can also use them in lighter weight fabrics, such as clothing, with solar threads or fibers. So this could help power IoT devices. I'm getting some echo all of a sudden from somebody.
That's Dean.
So this could help power Internet of Things devices that you carry or wear. And I want to talk a little about these four topics with solar textiles. Thin film PV cells, you saw photovoltaics being printed on flexible plastic. These are often less than 1 micrometer thick, and it allows them to be flexible while still capturing solar energy. So these can be attached to fabrics or printed right on the fabrics. Organic photovoltaics are made from carbon-based polymers, and they can be produced using printing techniques like those used in the textile industry. You can print those directly on the fabrics. Dye-sensitized solar cells, DSCs, also known as Gretzel cells, use dye molecules. So there's special dyes that can also absorb light and generate electricity. When light strikes the dye, it releases electrons into a titanium dioxide, and that can generate an electric current.
That's actually being used on houses in some areas and on vehicles. That's cool.
Yeah, you can kind of paint them with this dye, and it'll actually conduct electricity.
That's awesome.
How do you put the electrons back in the dye?
Well, it's like the solar panels work. There's a there's something applied to it that makes the electrons move in one direction and the holes move in the other, like a magnetic type of a force, and that creates the current that produces the electrical power. These dye sensitized, these DSSCs can be flexible as well as translucent, so you can at least get some light through them as well as the light that gets absorbed. And the perovskite solar cells are compatible with these flexible substrates. So they can be also used in fabrics or textiles. The problem is, as we mentioned before, that perovskites are sensitive to moisture and high temperatures. Couple other things I wanted to mention. When you're using thin film PV cells, the cells are typically made from amorphous silicon, cadmium telluride, or copper indium gallium selenide, CIGS. So there's several kinds that can be used. And the challenge lies in creating the connections between the cells in these fabrics that can withstand the bending and folding of the fabric without breaking. So that's where certain special kinds of threads and materials like that are used.
Tom, just a quick point. I'm sorry for jumping in, but just make a little quick points. We had a solar clothing fashion show a few years ago, working with the University of Minnesota, and they incorporated solar into clothing that they were designing. So it's pretty awesome.
Yeah, if we're talking about clothing, that can actually be used to charge up your devices.
Yep.
The phone you carry or the watch you wear or something like that.
Yeah.
OPVs, organic photovoltaics, while they're less efficient than inorganic ones, their flexibility and potential for low cost, high volume production do make them promising for solar textiles. The DSSCs mimic the photosynthesis process used by plants. It's a layer of titanium dioxide nanoparticles coated with a light-sensitive dye. So it's surrounded by an electrolyte solution. So when light strikes the dye, it releases electrons into the titanium dioxide. That's maybe a better description of what you were asking about, Tom. And that generates an electric current. So these DSSCs can be used on windows since they're flexible and translucent, especially like greenhouses where curved windows and so forth. And the perovskite solar cells can be manufactured using low temperature processes, which do make them compatible with flexible substrates. So biophotovoltaics, I do want to show a short video on that. I think I have time. And then we'll get into space-based. So, see, I have to bring up this video. Okay, the rest of this video is about using algae to produce hydrogen, which is not our topic today, but it is an interesting topic. So basically, this is maybe the ultimate green energy source. There aren't any precious metals involved, and although it doesn't produce a great deal of electrical power, at least in these early stages of experimentation, it is ecologically very, very good compared to any other um, source of electrical power. So, are there any questions on that? Your hand is up, Carol.
Oh, sorry, that's still up for, I want to see your power from space with,
The one thing about that, Tom, is that in Minnesota in the summer and late summer, we could produce a lot of energy because we have so much algae.
Yeah, I was going to say that.
Yeah. Apparently some types of algae work a little better than others. So it might not just be any old algae, but
Seems like that would be an ideal problem for DeepMind to work on to optimize the design or genetic engineering of algae for that purpose.
yeah. Yeah, AI could help there.
Is there
Possibly.
some way to take apart a snow crystal and get energy out of it?
Uh,
Not that I know of.
Yeah, you melt it, run it through a generator.
Energy return on energy investment is a serious concern
Oh,
with
David.
snowflakes and algae.
Yeah, I think you wouldn't get as much out of it as you put into it. Okay, so a little more about the future, I've been talking about current research that may, within the next 10 or 20 years, be realized and be available to everybody. By 2050, solar will become the dominant electrical energy source. At the rate we're going, let's see. I guess, yeah, I'll just read this. 30 up to 45% of total generation will be solar by about 2050. This is an increase of 20 times to of its current capacity to over 14 terawatts. This efficiency will exceed 35%. Right now it's under 30%, and the cost will be 70% lower than it is now. So it'll be better and cheaper. And that's why it's going to be the dominant electrical energy source within 10 to 20 years, 25 at the most. About 1/3 of the capacity produced of this 14 terawatts, about 5 of it will probably be stored in batteries or stored in other ways, used pumped water systems or whatever, to manage intermittency. So when you don't have sunlight, you get the battery, the energy out of the batteries where it was stored when you had plenty of sunlight. There have been times when we've had more sunlight than we needed. That happened in California not too long ago. So since they didn't have enough storage for all that power that was being produced from solar, they had to cut back on the production. So there was opportunity wasted there. That's happened in a few other places too. They produce more renewable energy than they could use. So that's why storage devices and distribution are pretty important. Okay, yeah.
One of the potential other ways to store that energy is to either electrolyze water.
Yes.
Yes, you can produce hydrogen, yes.
Yeah.
Yep.
Or you can process carbon dioxide into natural gas and potentially some form of carbon like graphite or graphene that are more valuable. So there are some other possibilities for storage besides just batteries and pumped water, pumped air.
Yes. I think I'll probably be doing hydrogen next, and I'll be talking about that. Because it takes energy to produce the free hydrogen.
Oh,
And where does it
absolutely.
come from? This could be one of the main sources of that energy. Excess solar during the certain times.
Or wind, like out at Morse.
Yeah,
Well,
excess wind, yeah.
RethinkX is talking about this being a feature of renewable energy rather than a bug.
Yeah. Yeah, it can be used to produce another form, a very convenient form actually, of electrical power, namely the hydrogen.
Well, or energy storage. And the natural gas distribution system we have currently is a form of storage.
Yes. In fact, there are two ways natural gas is used. One is for peak times when we need more power than we're currently producing, and that's more expensive to turn those plants on and off. And the other is for steady state production, you might say.
Another form of storage that's really unique is in one of the co-ops in Minnesota. Actually, a bunch of them have used hot water storage as a way to store energy. And they're selling people hot water heaters at a very low price, and that's how they can save energy and store it. So interesting.
Yeah. Okay.
You
I'm
you
nearly
could
on
also
time. Go ahead.
you could also use the excess energy. It sounds very strange to say that. And use it to pump water up into a reservoir
Yeah, I mentioned that
and,
earlier.
and let it come down earlier. But from space, you could take and heat the water in the reservoir.
Yeah. Okay, we're almost to 12. I want to get to space-based here.
Yeah, keep Carol happy.
Yeah. Okay, this concept of space-based solar power has been around for about 80 years, ever since Isaac Asimov first used it in a science fiction novel. It's been considered seriously for the last 50 years or so, 50 to 60 years. And there's two ways you can do it. The most promising to me looks like large satellites in geosynchronous orbit, which can generate quite a bit of power and beam it down to Earth as microwaves. Microwaves are very good for this because basically the atmosphere is invisible to them, and the moisture. So they don't lose much energy getting beamed down to the Earth. The other option is low Earth orbit satellites, which can be much smaller, generate smaller amounts of power, and they would transmit the power down via laser beams rather than microwave beams. The problem with this is it's quite a bit less efficient because operating laser beams takes a lot of power, and there's at least as many conversions of power to do it that way as it is in the other way, transmitting microwaves. So those are the two main options, and the antennas for the first option, you have to have very large antennas because these aren't collimated beams like lasers, and they're transmitted from very far above the Earth. So by the time they get down to the Earth, they're dispersed. They're not going to fry you or fry any birds flying through the air. It's not that kind of power. So you have very large antenna fields to receive these transmissions, and they can be as someone said as big as 5 to 10 kilometers square. so that takes up a fair amount of space. The low Earth orbit satellites transmitting power via laser beams can use very much smaller antennas, probably on the size of maybe a pickleball court or half a pickleball court, somewhere around there. Just a little bit of what's happened so far. Japan actually did a demonstration project just last year, late last year, called the Ohisama project. It was basically a feasibility test. They launched a small satellite with solar panels that collected energy in low Earth orbit and converted it to microwaves and beamed it down to a ground receiver. And that was successful. It was only 1 kilowatt of power, but it was a demonstration that of feasibility, basically, that this could be done. Chinese have big plans. They plan to have a 10 kilowatt satellite in low Earth orbit within the next couple of years, and a 1 kilometer wide solar array in geosynchronous orbit by 2030. And that one would be capable of 1 megawatt of power. What they've been talking about can be as large as 2 gigawatts. So much larger than even the one that China's planning. But we'll see how feasible this is as we continue researching this and putting more satellites up there. So this is not an impossible technology. It does have its limits and its pros and cons, which I'll get into in a few minutes, but I did want to show, I have 3 possible videos. 2 of them are over 15 minutes long and one's a little over 6 minutes long. But the one over 6 minutes long is titled "Space-Based Solar Power is Dead." So it's kind of, it talks about the disadvantages of space-based solar, so it's not a real balanced one. But I don't really have time, since it's noon now, I don't have time to show the 15-minute ones. So I'm going to show the one, it'll give you some taste of what it's about. This is Sabine Hossenfelder. She's kind of an iconoclast, she's also a physicist. I'll get to your questions in a minute. And she had put out in early 2024 a video that was very good, called "All You Need to Know About Space-Based Solar Power." And then a few months after that, in May of 2024, she put out this one called "Space-Based Solar Power is Dead," because of certain developments that I guess had happened. So I'll take a couple more questions, then I'll show that last video. And there are 2 other videos that I think you would want to look at. One is another Matt Ferrell one from his Undecided series, called "Why Space Solar Might Finally Work, But Not How You Think." And that's the one that talks about low orbiting satellites and using lasers. And he talks somewhat about how the American military is very interested in those, because they could be used to charge drones or supply power to units in the field, so that are basically off the grid. So that's an interesting one. And the one, "All You Need to Know About Space-Based Solar Power" by Sabine Hossenfelder is another one I recommend you look at. Take a couple more questions, and I'll show this one last 6-minute video. So go ahead, Doug.
I just wanted to share with people something that I think is interesting that kind of pertains to what you know, XL Energy up at Becker, Minnesota is in that area is putting in like 1 million solar panels. And like everything, it needs maintenance. And what they've set up is a number of drones that are nested in one location. Those drones go out and automatically scan along all those panels. That's a lot of them to do. I think it's like 6 drones or something like that. They're programmed to take a certain course. Then they're looking for hot spots in the panels where it shows that there's a problem. And then they come back to their nest and they set overnight, download their information for the engineers to look at. And the next day they go out and do it again. So it's really a interesting technology where, solar and drones and, a bunch of things are coming together. So it's to me pretty interesting how they're, they're doing it. So that's it.
Okay, Eric.
Well, any broadcasting down huge amounts of power by a microwave is going to heat up anything that has water, like the atmosphere, and that's not good. But as Elon explains it in his daily postings, an increasing part of the total power demand is for data centers.
Yeah.
Those data centers will, he said, probably 4 or 5 years, will be practical when they get the lift costs down to build the whole data centers in space themselves, and then directly power them in space and just send the input up and probably lasers, and then output back down in lasers, which wouldn't necessarily heat up the Earth. So that would be a major way of using solar power, continuous free solar powers, uninterrupted solar power, to take a lot of the load off of Earth's production.
Yeah, that sounds pretty reasonable, except that's a lot of mass to put up there in space.
Well, it's getting down. He's getting with those. Have you seen those giant spaceships? And he's going to be building thousands of them a year, and you get enough economies of scale. He said it's probably about 4 or 5 years.
It's getting easier and cheaper to launch stuff.
Yeah,
a lot cheaper than it used to be. So
yeah. He said 4 or 5 years it'll be. I think it'll be practical.
Yeah, I was worried at one point about microwaves being beamed down also.
Yeah.
But if you look at these other videos that I won't be able to show, the one by Sabine Hossenfelder, especially, since she talks about geosynchronous orbit satellites sending down microwave beams, there is no real problem with interaction in the atmosphere with you.
I wonder why not. How it's not going to heat up the water vapor in the atmosphere.
And it depends on the exact frequency you're using of light. Okay, before I show this last video, I just want to quickly run through what the advantages and disadvantages are. Okay, the advantage of space-based is that it's constant, it's 24/7 generation, especially for the geosynchronous ones, because they're in a place where they get sunlight almost all the time. There are 2 couple-week periods during the year when it's somewhat intermittent, where they do fall into a shadow, but otherwise it's pretty much 24/7 generation. You can have higher energy intensity impinging on the solar panels because sunlight's more intense in space. So it's because it's not absorbed or scattered by the atmosphere. So you get higher efficiency per square meter of solar panel. Global energy distribution. The satellites can transmit power via microwaves or lasers to specific locations on Earth, even remote or disaster-stricken ones, which can offer flexibility and energy security. Zero emissions. As a clean, renewable resource, there are no greenhouse gases produced, and this can reduce the need for large land-based solar farms, also, which can protect ecosystems. But on the other hand, for these geosynchronous microwave systems, the antennas do have to be very large, up to the size of decent sized islands, maybe half the size of Manhattan, for example. Energy independence. So reliable independent power can be provided to regions that would otherwise be off the grid, and this can reduce geopolitical competition for limited resources that give us energy. And high efficiency and lower material usage, because the operation is nearly continuous. These systems can achieve higher capacity factors than ground-based renewables if they last 100 years or so. But now we get to disadvantages. Okay, solar storms is one possible one. We're just past the peak of solar cycle 25. That was at the end of last year. We may be due for a Carrington level event sometime, but that it's not anticipated. Carrington level event is one that'll knock out all the electronics in the world.
Now, how predictable is that?
Well, right now
Not.
they've estimated its occurrence within the next 4 or 5 years by 2029 is less than 2%. But it's hard to be. We're kind of due for one. It's been a few hundred years, a couple hundred years, I think, since we've had one. Getting large solar collectors into space, especially for the geosynchronous ones, they are several kilometers wide and can weigh several thousand tons. Now, as materials improve for the photovoltaics, that weight can come down some, but still, it would take several trips up there to provide the materials for one of these solar collectors. And they would probably be put together by robots. It's somewhat inefficient because what you have is several conversions. You have these photovoltaics collecting the sunlight, creating electricity, converting that to microwaves or laser beams to send that power back down to an antenna that then converts it back to electricity. So you lose some efficiency. Another big one for these things out in space is you have radiation, dust, and space debris that will affect them to some extent, which means they will require maintenance. And maintaining things that are long, 100 miles or maybe thousands of miles away is not easy. Land use. For the geosynchronous microwave satellites, you need large antenna fields, as I talked about before. Maybe something on the order of 10 square miles. So they do take up a lot of space. For the geosynchronous ones, there are big temperature swings, a couple weeks, twice a year, as they go in and out of the shadow. And that temperature swing can be up to about 200 degrees Celsius. And that can affect the structure and the electronics. So that would be another maintenance problem, possibly. There's another one. You have to orient the panel toward the sun, but you're aiming the beam in a different direction down toward the Earth, and that's changing all the time. It's tougher for the low Earth orbit satellites because not only are they aiming in a different direction with the sun as they move, but they're aiming at a different direction. They're moving over the Earth at 90 minutes per orbit or something. So they have to have very accurate aiming and be able to adjust it on the microsecond or nanosecond scale.
articulated satellites.
Yeah, there's one company that has a kind of a helical design to their collectors that says they can and they can direct the beam electronically. So they're saying they can avoid some of that problem. And so they have less mechanical stuff going on. But we'll see how that pans out as they try to test it. And there's competition for space-based solar, namely Earth-based solar. And that's getting cheaper all the time. So whether the space-based solar will ever be viable compared to Earth-based is a question. And the low Earth orbit with lasers, as I mentioned, using lasers is quite inefficient. They take a lot of energy. And there's a lot of debris there. So it's likely that they'll need even more maintenance than, or have shorter lifetimes than satellites up at geosynchronous orbit. So that's a kind of a list of the advantages and disadvantages.
Tom,
yeah.
One advantage that I just checked on, these solar panels on Earth, like you say, are running around 20%. And I just checked on what they're running at it on the space station, and it's at about 35%. So that kind of differential.
That's the low temperature that helps.
Yeah.
As technology improves, that gap will close. In fact, using perovskites and graphene and so forth, that can bump up the Earth-based ones a fair amount right now. But yeah, currently they are quite efficient. In fact, Voyager 1 and Voyager 2, they're way out there at the edge of the heliosphere, and they don't have much power, but they're still getting some apparently.
Mm-hmm. I believe they
not very old
aren't they both radioactive powered?
It could be. Yeah, maybe it's not solar. You're right. Okay. Let me stop sharing this. And if you guys have time, I'll try to show this 6-minute video.
Yes.
For sure.
Yes.
Please.
Okay, but I do recommend you look at the other two that I listed on the meetup site. So she's kind of pessimistic about space. And she doesn't mince words. Okay, but that followed by a few months her other video that I listed in the longer video that I listed on the meetup site. So you might want to watch that one. It wasn't quite as pessimistic.
Tom, I got to go. This is Doug. My wife just got put in a nursing home. And so thank you so much. Fantastic presentation.
Thank you. And sorry about your wife. If there are no other questions, I guess we're done. What's up next week, David? Do you have a question, Carol?
Tom Petty, Dean Petty is going to be doing medical advances, positives, negatives, and economics.
Okay, Carol.
Yes, some of you may remember my last presentation on space-based solar power, in which there was a very blue sky suggestion that, okay, we have this counterintuitive notion that global warming will lead to the destruction of the Gulf Stream and therefore make Northern Europe freeze over. And this could be avoided by, again, space-based solar power heating up the North Atlantic. Just enough to produce more rain over the Middle East. This will have the effect of, okay, the destruction of the Gulf Stream is likely to come from too much fresh water over the North Atlantic.
Yeah.
And if you heat this up to produce rain, you know, you're creating a giant desalinization plant, and the water in the North Atlantic is becoming less fresh water, more salty. So you do two things. By beaming a lot of power, you know, right into the North Atlantic where the Gulf Stream hits, you know, Norway and Sweden and England and places like that. It has real possibilities.
Sounds
I
complicated.
don't know if the rain production would be enough to offset all the ice melting up there, but interesting idea.
Well,
Saltwater rain sounds like fun too.
what?
Well, no, the salt would stay in the water.
Extra
Yes.
heat that you bring into the atmosphere is going to spread around to the rest of the world.
Well,
Yeah.
that's what the Gulf Stream does right now,
Well,
is it spreads
Yeah.
equatorial heat up to the North Atlantic
Mhm.
places.
but there's a
Yeah, even though most of Europe is north of us, it's a more moderate.
yeah.
Yes, I mean, if you remember from your history classes, the pilgrims who came over here were expecting Maine to have the climate of southern France because they're about at the same,
Latitude.
yeah.
Latitude.
And unfortunately, southern France is getting the advantages of the Gulf Stream, and Maine is not. So, you know, this is really a significant possibility, guys.
Yeah, that's redistributing the existing amounts of influx of heat. You're talking about adding more heat to the world overall, and it will tend to.
No, I'm
Well,
not
yeah.
talking.
Well, you're
I am
talking about
talking
heating the
about
water.
doing exactly the redistribution that is currently being done by the Gulf Stream.
But you are talking about adding heat to evaporate the water.
Say
It'll
again?
be
You're talking about adding heat from the space, though, net
Right.
increase in the heat impeding
Using
impinging on
microwave
Earth.
beam from space to heat up the water. So you're adding heat.
Yes.
That
Well,
will
it's going to be
dissipate.
interesting, Carol. See you all next week.
I got a semi-humor, semi-serious. You know, maybe the real reason that Trump wants Greenland is, well, first I have to prefix it a little. My friend's friend who made desalinization practical by osmosis, he also discovered the possibility, a potential of extracting energy from mixing fresh water with salt water, and which is close enough to practical that Norway has hired him to study that for them with them, and they haven't done anything yet. But and Greenland has vastly more, I think, fresh water mixing with salt water every year during the melts, and it's cold. You could build data centers there, use that somehow if you could get that different. And data centers, a lot of huge energy has to be expended cooling them. Well, Greenland's much cooler than most of the world, so I wonder if that would be, maybe that's the real reason he wants Greenland, to build huge data centers there powered by,
Well, that might be why Bezos and those people would like it, but I think Trump wants it for the minerals.
What?
The minerals.
Oh, yeah,
that's part of it. And also the, just
particularly the lanthanides.
yeah. And the corruptibility, if you only got 57,000 people, it would, if China gets enough money, it pays them, the rulers there enough money, say they get independent.
He's not worried about Russia, like he says, because he's buddies with Putin, but.
Well,
Not really,
it's also true that he could achieve the same security ends.
I think he just knows that we need their 5,000 nukes, use them as cannon and fodder too. And for their death struggle with China, we desperately need Russia's 5,000 nukes to help out because we're falling behind China.
We're setting a bad example by invading Venezuela, and that might encourage China to invade.
Yeah.
Well,
but anyway, I need to go.
Okay.
Thanks.
Yeah.
See you next week.